Alright, welcome back guys. We're going to finish up section 3.2 on conditional probability. Now we're going to look at the multiplication rule, and this is really the same rule that we've seen before when we would to determine, well, except it's in the context of probability in this case. Okay, so we're not trying to figure out the number of ways 2 or 3 events can occur in sequence. We're trying to figure out what's the probability that 2 events will occur in sequence. So the probability, not the number of ways. But in doing some of these, sometimes you do have to determine the number of ways that an event can occur to be able to determine the probability, as you guys know. But anyway, so the probability that 2 events A and B will occur in sequence. Okay, so this is sometimes referred to as an intersection. In other statistics books, you would see this referred to as the probability that event A intersects event B. Okay, but anyway, you're going to read this: the probability of A and B occurring. Okay, so event A occurs and then event B occurs. And this is going to be the probability that event A occurs times, so this is where the multiplication rule comes into play, the probability that B occurs given that A has already occurred. Okay, so this is the formula that you're going to use if the 2 events are dependent. And then if the 2 events are not dependent, meaning they're independent, then it's just going to be the probability of A times the probability of B. Okay, because the probability of B occurring given that A has already occurred is still just going to be the probability of B, because the fact that A has already occurred has no bearing on or has no influence on the probability of B, because they're independent events. The occurrence of one doesn't affect the likelihood of the occurrence of another. Okay, so anyway, so if you look here, it says to use it, you're going to find the probability that the first event occurs. Then you're going to find the probability that the second event occurs given that the first one has occurred. Okay, so here's that conditional probability. And then you're going to multiply these 2 probabilities. Okay, now remember, if these 2 events are not dependent, then this second probability is just going to be the probability of that second event. It's not going to be a conditional probability. All right, so let's look at some examples then. So, example 7 here, it says 2 cards are selected from a standard deck. So we're assuming we're going to select 1 card, and then we're not going to replace it, okay? Because if we replace it, then we're going to have independent events. So we're not going to replace it, and then we're going to select a second card. So the first card is going to be a king, and then the second card is going to be a jack. So what we're trying to find is this: what's the probability of selecting a king and a jack? Okay. So using that formula, this is going to be the probability of selecting a king times the probability of selecting a jack given that a king has already been selected. Okay, all right. Well, the probability of selecting a king, guys, is going to be 4 out of 52. There's a total of 52 cards, and 4 of them are kings. Times, now the probability of selecting a jack given that a king has already been drawn. This goes back to what we saw in the first part of this section. So if the king has already been drawn, then there are only 51 cards left. Okay, so again, the sample space is getting reduced here in a sense. So now there's only 51 cards left, but there are still 4 jacks. So 4 over 51, that's the probability of drawing a jack given that a king has already been taken. Okay, and then if we multiply these, we're going to get 16 over whatever 52 times 51 is. 2,652. Okay. And this is a fraction, you know, you could reduce if you want, guys. But I'm just going to put this in the calculator. I've already got the 2,652 in there, so I'm just going to say 16 divided by, and then if you go to second and the negative key right here, it'll reference this previous number. And so this is going to give us 0.006. If we go to 6 decimal places, that's what it would be. Okay. So this is roughly, as a percentage, this would be like 0.6% if you multiply by 100. Okay, but anyway, number 8, a coin is tossed and a 6-sided die is rolled. Find the probability of tossing a tail, which we'd call event T, and then rolling a number greater than 2. Okay, so I can denote this like this. I can say the probability of tossing a tail and rolling a number that's greater than 2. So I can use the greater than symbol and put a 2 in here. Okay. Now let's think about the nature of these two events. Tossing a head, regardless of the outcome, or not tossing a head, but tossing a coin, regardless of the outcome, has no bearing on the outcome of rolling a die. Okay, so these are independent events. I'm going to put this in the notes. So because of that, guys, this will simplify down to the probability of T times the probability that you roll a number greater than 2. Okay, so this second probability is not conditional because these two events are not dependent, they're independent. All right, well, the probability of rolling tossing a tails is 1 out of 2, or 0.5. I'll just put 0.5 times, well, no, actually let me do a fraction because 1 out of 2, okay? And then the probability sorry about that. And then the probability of rolling a number that's greater than 2 on a die, well, the numbers that are greater than 2 are 3, 4, 5, and 6. So that's 4, okay? So 4 out of 6. And so if we multiply these, we're going to get 4 out of 12. And as a decimal, guys, this is that, you know, the 0.3 that just goes on forever. So if I round it to 3 decimal places, then it's going to look like this. So it's a third. All right, we'll keep going. Number 9 here. So we're going to be using this Venn diagram to help us visualize this. So it says in a survey of 510 adults, in a survey, 510 adults were asked whether they drive a pickup truck and whether they drive a Ford. The results showed that 3 in 10 adults surveyed drive a Ford. And then of the adults surveyed that are driving Fords, 2 in 9 of those drive a pickup truck. And so what we want to do is find the probability that a randomly selected adult drives a Ford and drives a pickup truck. Okay, so I'm going to denote this probability. They drive a Ford and I'm just going to put truck, okay, for pickup truck. All right, well, this will be equal to the probability that they drive a Ford times the probability that they drive a truck given that they drive a Ford. Okay? So these are dependent events. Okay, so the probability that they drive a Ford, well, it's given to us in here because it says that 3 out of 10 adults drive a Ford, so that's 3 out of 10. Times, now the probability that they drive a truck given that they're already driving a Ford. So that's right here, because it says, of the adults surveyed that drive a Ford, 2 and 9 are driving a pickup truck. Okay, so again, this conditional probability is like we've narrowed the sample space. We're only looking at those adults that are driving Fords and trying to figure out, well, if you drive a Ford, what's the probability that it's a truck and not a car? Okay, so that's going to be 2 out of 9. And so if we multiply, we're going to get 6 over 90, and we'll see 6 divided by 90. This is going to be approximately 0.067 if we round to 3 decimal places. 0.067. All right. Well, let's continue. Number 10 here. So we're taking a multiple choice test again, a quiz, and there's 4 questions, and each has 5 answer choices. So a student is going to guess on each question, and there's only one correct answer. Okay, so this is a typical multiple choice quiz. So the part A, we want to find the probability of answering the first question correctly. Well, there is just one correct answer out of a total of 5, so it's just going to be 1/5. Or as a decimal, it would be 0.2. Okay, you basically have a 20% chance of getting that first question correct. Now, part B, find the probability of answering the first 2 questions correctly. Okay, all right, so let's think about this. This essentially would be like this: the probability of answering number 1 correctly and number 2 correctly. Okay. Well, these are independent events. We're assuming they're independent events. I mean, I guess it's possible that one question could build on another, but that's not what they're wanting us to assume here, guys, by the nature of this question. So I'm going to put up here that we can look at the outcome of answering each of these questions as an independent event. Okay. All right, so because of that, this is going to be the probability of answering the first one correctly times the probability of answering, the second one correctly. Well, the probability of answering the first one correctly is 1 out of 5 times the probability of answering the second one correctly is still 1 out of 5. Okay, so this is going to give us a total a product here of 1 out of 25. All right, which is, as a decimal, guys, this would be 0.04, okay, or 4%, in other words. All right, what about part C? Find the probability of answering all the questions correctly. Okay, well, this is going to be the probability of answering the first one times the probability of answering the second one correctly times the probability of answering the third one correctly, etc. Well, because these are all independent events, it's just going to be the probability of answering each one correctly, which is going to be 1/5 times 1/5 times 1/5 times 1/5 times 1/5. Or in other words, 1/5 to the 5th power, okay? Yeah, so 1/5, guys, is 0.2. Now, if I raise that to the 5th power, now when you see this, this is what's referred to as scientific notation. I think I may have discussed this earlier, but what's going on here, what this means is 3.2 times 10 to the negative 4th. I'll even put this in the notes, 3.2 times 10 to the negative 4th. So to write this in standard notation, what you actually do, since this exponent is negative 4, you move that decimal to the left 4 places. So if I were to do that, I would end up with 3 zeros and then the 3, 2. Okay? So on one like this, rounding it to 3 decimal places might not be enough. We might have to round it to 4 decimal places. But anyway, this probability is very low, as you can imagine. So intuitively you know this. Let's say you take a quiz in this class that has more than one question. And you just guess on every single one. The chances that you're going to make 100% on that quiz are very low. Okay. All right. Okay, what about part D? Find the probability of answering none of the questions correctly. Now, you might be tempted to think, well, here we could implement the complement. We could say, okay, 1 minus the probability of getting them all correct would be the probability that we get none correct. But that's not right. Okay? The complement to getting them all correct is, it could be missing all of them, but it could also be getting 2 of them right and 3 of them wrong. Okay? So anyway, what we're going to do is figure out the probability of answering each question incorrectly. So for the first question, we know 1 choice is correct out of a total of 5. So that must mean that 4 choices are incorrect out of 5. And then the same thing for the second one. There's 4 incorrect choices out of a total of 5. And you just keep doing this. Okay, because there's 5 questions. Actually, I actually read this incorrectly, guys. There's only 4 questions. So let me alter this last example. Okay, it's not going to be this. If there's only 4 questions, then you would only be raising that to the 4th power. Let's go ahead and fix this. So 0.2 to the 4th power. There we go. 0. This is small still, but okay. Which, by the way, the shorter the test is, or the quiz, the fewer questions it is, the more likely you are to be able to actually guess and get every single one correct. All the way down to the quizzes that we take, or that you guys take. If it's a true-false quiz, it's only 1 question. You have a probability of 1 out of 2 of answering it correctly. So, anyway, I think the fact that there were 5 choices kind of threw me off into thinking there were 5 questions. But anyway, just continuing here. So there's not going to be 5 questions. There's only going to be 4 questions. And the probability of answering each one of those incorrectly is 4/5 times 4/5, etc. And this would end up becoming 4/5 to the 4th power. 4/5 is the same as 0.8. If I raise that to the 4th power, we're going to get 0.4096. Okay. Now this is kind of interesting because obviously this probability is a lot higher than the previous probability. But, it would take some skill, I guess, for lack of a better way of saying it, if you're guessing, to actually answer every single one incorrectly. Okay? If you're just guessing, it seems like you're fairly likely to get at least 1 correct. All right, so what about the last one, part E here? Find the probability of answering at least 1 of the questions correctly. Okay? So this event right here is actually the complement to answering all the questions correctly. So if you don't answer them all correctly, you at least answer one correctly. Okay, one correctly, or two correctly, or three correctly, or anyway. So we can utilize the complement here. So the probability of answering at least one of the questions correctly. No, actually, I think I said that wrong. No, this is the complement to answering none of them correctly. Okay, so this is going to be 1 minus the probability of answering none of them correctly, which we just found. The probability of answering none of the questions correctly is this 0.4096. So this will be 1 minus 0.4096. I can actually, again, use that same number, so this will be 0.5904. Okay, so it's these two events that are complements of each other. You either answer at least one correctly, and so that could be 1, 2, 3, or all of them correctly, or you answer them all incorrectly. Okay, so each of these is a complement of the other. So anyway, here's another instance in which finding the probability of something is actually easier done by knowing the probability of its complement. Okay. All right. We'll continue. Number 11 here. The probability that a household in the U.S. owns a dog is 39%, or 0.39. So 3 unrelated households in the United States are selected at random. Okay, so probably the events here are going to have to do with determining whether each of these 3 households has a dog or doesn't have a dog. Well, the fact that these households are unrelated, guys, that's an indication that these events are probably going to be independent as well. Okay. So the probability that all 3 households own a dog. Well, if these are all independent events, then we could say the probability that the first one owns a dog times the probability that the second one owns a dog times the probability that the third one owns a dog. Well, we know what the probability that the household owning a dog is. It's 39%. So this would be 0.39 times 0.39 times 0.39, or in other words, 0.39 or 39% to the third power. This one is very similar to the previous example. All right, so if we round this to 3 decimal places, we're going to go 0.059. Okay, and the overall probability decreases each house that you add. Okay, what about part B? Find the probability that none of the 3 households own a dog. Okay, so we need to think about the complement here. So the complement to owning a dog is not owning a dog. So the probability of not owning a dog is going to be equal to 1 minus the probability of owning a dog, which is 39%. And so if you do this, guys, you're going to get 0.61. So this is the probability of not owning a dog. So the probability that none of these households own a dog is going to be 0.61 times 0.61 Find 0.61, okay? Or in other words, the probability that the first house doesn't own a dog times the probability that the second house doesn't own a dog times the probability that the third house doesn't own a dog. So this is going to end up being 0.61 to the third power, or 61 hundredths to the third power. And let's see, to 3 decimal places, this would be 0.227. Okay. All right, and then very similar to that last one, find the probability that at least one of the 3 households owns a dog. Well, that's going to be the probability, well, it's already written. I have it already written here. That will be the probability that, so the probability that at least one household owns a dog is going to be equal to 1 minus the complement, which would be the probability that none of the households own a dog. So 1 minus the probability that none own a dog we just found. It is 0.227. Okay, so if we subtract these, we're going to get 0.773 to 3 decimal places. Okay, because these events are complements of each other. The complement to all 3 houses not having a dog is that at least one of those 3 houses has a dog. One has a dog, or maybe 2 have a dog, or all 3 have a dog. Okay. All right. Well, I think we've got one more here. We're going to be using this table for. This one's similar to one we saw previously. So the table shows the results of a survey in which 90 dog owners were asked how much they spent in the last year for their dog's health care, and whether the dogs were either pure breeds or mixed breeds. Okay. And so you can look here. So it looks like there's a total of 90 dog owners. So 40 of those 90 spent less than 100 in health care. And then 50 of those 90 spent $100 or more in health care. And then of the 90 that own these dogs, 54 of the dogs are pure breeds, and then the other 36 are mixed breeds. So part A, find the probability that $100 or more was spent on a randomly selected dog's health care in the last year. Well, for this one, guys, you're going to be looking at this row right here. This is the row that contains the breed mixture here, no pun intended, of those that $100 or more was spent. Okay, so there's going to be a total of 50. Wait, no, that's not correct. I'm sorry. Not sure what I was thinking there. So the probability that $100 or more was spent on a randomly selected dog's health care. Well, you're going to look in this column right here. Of the total 90 dog owners, 50 of them spent $100 or more. So it's going to be 50 out of 90. We could write it like this. The probability they spent greater than or equal to $100 is going to be 50 over 90. Which is a decimal. This is the same as 5 divided by 9, by the way. It's going to be 0.556 if I round it to 3 decimal places. Okay, what about part B? Given that a randomly selected dog owner spent less than $100, find the probability that the dog was a mixed breed. So guys, whenever they say this part right here, given that means this is like conditional probability, sort of. So our sample space is going to get decreased in size. So now when it says given that the dog owner spent less than $100, we are only looking in this row. Okay. So now what are we trying to find? Of these that spent less than $100, what's the probability that the dog was a mixed breed? Well, there's a total of 40, and 21 of those are mixed breeds. Okay. So we could write it like this: the probability that the dog is a mixed breed, given that less than $100 was spent, this is going to be 21 out of 40. Which is 0.525. All right, and then part C. Find the probability that a randomly selected dog owner spent less than $100 on health care, given that the dog was a mixed breed. Okay, so here again, this is conditional probability. The probability that they spent less than $100, given that the dog was a mixed breed. So this is kind of like the reverse of the last one, isn't it? So what you're going to do here is, since we're only considering the dogs that are mixed breeds, you're only going to be looking in this column. Okay? So there's a total of 36 mixed breeds. Now, of those mixed breeds, 21 of their owners spent less than $100 on health care. So this is going to be 21 out of 36. And this would be .583. Okay, to 3 decimal places. All right, so your homework problems, guys, are going to be similar to these. Okay, so just refer back to your notes. And also, because your notes are Word files, rather, you should be able to click on this. This is kind of an interesting little video, and it has to do with the probability that LeBron James will make 10 free throws in a row. Or I believe that it's been a while since I've watched it. I used to show it to my classes that I taught on campus, but anyway, it's kind of fun to watch because it deals with this whole idea of dependent versus independent events. Okay, and you're also utilizing the multiplication rule as well. So anyway, you can watch that if you want. But anyway, that concludes this section, guys. I hope that I did not go too fast. And I'll see you in section 3.3.